Right, go right ahead.
Thank you very much for that introduction, Dr. Malek Ahmadi. Going to go ahead and share my screen here. So I'm really excited to chat with you all today, and I'm particularly excited for the Q&A at the end. I'm going to hope to save enough time for us to have a discussion because I'd really like to get your feedback on this work and some outstanding questions I have. So today I'm going to be discussing tau PET thresholding methods, both a review as well as an empirical investigation of these different methods, and discuss some of their implications for ATN classification, which I'll discuss shortly. So just as a general overview, I'm going to start with some background on Alzheimer's pathology and how that relates to ATN classification, talk a little more specifically about tau PET, which is the methodology that I used in the two studies I'll be discussing today. Then I'm going to go through a review of existing tau PET thresholding methods pretty briefly, discuss some comparisons of specific cut points using different methods, and then considerations for this research. I'm then going to shift my focus a little bit to discuss ATN classification again, with a specific focus on discordant, amyloid and T-tau classification, doing some comparisons across these AT discordant and concordant groups, and then talk about implications and conclusions, and lastly, open it up for discussion. So we can't talk about Alzheimer's without talking about the hallmark pathologies of Alzheimer's. Amyloid, tau, and neurodegeneration are three hallmark pathologies. There are, of course, many others, and many research studies have shown that there's actually a pretty wide pathologic presentation in Alzheimer's disease with different combinations of different pathologies. But for the purpose of today, I'm going to focus on these three, and in particular, tau. So tau is a protein that forms neurofibrillary tangles intracellularly that relates to Alzheimer's pathology and subsequent neurodegeneration. It's also hard to talk about Alzheimer's pathologic progression without talking about these canonical Jack curves. So this is a theoretical model of Alzheimer's pathology and the various presentation of these pathologies in terms of their temporal emergence. These Jack curves suggest that amyloid is the first protein to become abnormal within the Alzheimer's pathologic cascade, which then initiates tau pathology, working together to affect brain structure and eventually memory and clinical functioning. So really suggesting this specific temporal ordering whereby amyloid becomes abnormal first and tau and neurodegeneration happens subsequent to those amyloid changes. This relates to a more recent classification or Alzheimer's biomarker staging scheme called the ATN classification scheme. And ATN stands for those three pathologic hallmarks I mentioned: amyloid, tau, and neurodegeneration. And I'll be focusing more so on amyloid and tau in particular today. So you can see from the chart on the right here that there are 8 different classifications you can get with either biomarker positivity for amyloid, tau, and or neurodegeneration, or negativity for amyloid, tau, and or neurodegeneration. And this leads to different nomenclature used for these different groups. So you can see in the light gray box here that anyone who has abnormal amyloid or amyloid positivity as measured with biomarkers is considered to be on the Alzheimer's continuum. That's also represented here in the yellow circle, where anyone with amyloid pathology, regardless of the presence or absence of other pathology, is considered to either have Alzheimer's pathologic change or Alzheimer's disease. And one really important thing here is that you'll notice that in order to obtain these classifications, we have to binarize them into positive and negative values or groupings in order to create these stages and these classifications. Now, one of the ways we can look at these biomarkers is through PET imaging. There are other methods as well, such as cerebral spinal fluid and plasma markers. Today, I'm going to focus more on PET or positron emission tomography imaging. And here's a little bit of information about tau PET and some of its advantages. So tau PET allows for the in vivo characterization of pathology. So rather than looking at someone's tau pathology post-mortem, we can actually characterize it while they're still alive. This can improve the temporal disparity between cognitive and pathologic examinations. If we wait until someone has passed away in order to look at their brain, their most recent cognitive performance may have occurred years prior to their death. And therefore, it's hard to assess really that close temporal proximity between tau and cognitive changes. With PET, we can do those essentially concurrently, really in the same visit, doing a neuropsychological assessment and a tau PET scan so that we can assess for the associations between those two. With tau PET, the regional distribution of tau pathology can be assessed, as opposed to cerebrospinal fluid or plasma tau, which gives you one global measure of tau values. With tau PET, we can actually look at the regional distribution, which actually has been shown to approximate the neuropathologic staging scheme. Now, when we talk about tau PET, we can't really talk about it without talking about Braak stages, which reflects the stereotypical progression, spatiotemporal progression of tau throughout the brain. You can see in the top figure here, all the way on the left, that tau in Braak stage 1/2 begins in the entorhinal or medial temporal regions. In Braak stage 3 and 4, it spreads out to more lateral temporal, inferior parietal, and some inferior frontal regions. Whereas in Braak stage 5/6, at the later end of the Alzheimer's pathologic continuum, tau has spread pretty much well throughout the cortex. And you can see below those figures here that that's pretty well approximated by tau PET values, again, where we see medial temporal progression initially, moving out to lateral temporal and inferior parietal cortices, and eventually to the whole cortex in that Braak stage 5/6. So this is going to be really important for us to think about when we're creating these cut points, because we need to consider where in the brain are we looking for tau, and at what stage do we want to capture tau, earlier or later? And I'll be talking about this more as we go on, but just keep in mind this staging scheme of how tau progresses throughout the brain, beginning medial temporally and progressing cortically thus thereafter. So first thing I'm going to talk about is how we actually determine who is tau positive versus tau negative. And I'm going to do that by initially reviewing the literature on tau PET thresholding methods, then systematically deriving cut points using different thresholding methods and comparing those cut points on how well they can differentiate tau positive from tau negative individuals on various outcomes. And this is work that I conducted that's now published in Alzheimer's Research and Therapy earlier this year. So for this systematic review, I used the following search terms: tau PET positivity, tau PET threshold, tau PET cutoff, or tau PET cut point, to really capture all of those ways that we can create that binary variable of tau PET positive versus negative. And we replaced all the above terms with fluortaucipir, because this is the tracer that I was specifically focusing on for this systematic review, just to keep it consistent within one radio tracer. The exclusion criteria were if the studies already used an existing cut point. So this required that they create their own cut point or use their own thresholding methods. If studies used a continuous tau PET measure, because of course we're interested in looking at cut points here, studies were excluded if they thresholded in a non-binary manner, for example, creating subtypes. And that's because we really wanted to look at specifically just that binary variable of tau PET positive or tau PET negative. As I mentioned, if a tracer other than fluortaucipir was used. If studies focused on non-AD neurological conditions, for this systematic review, I was really focused more on the Alzheimer's pathologic continuum, and then excluded if studies were based on, or if they used animal models. So this was just focused on PET imaging in humans. Back when I did this search, there were 540 articles that matched any combination of the search terms. About 500 of these were excluded just from reviewing the abstract and identifying one of the exclusionary criteria that I mentioned, which resulted in 47 studies having their full text reviewed for the exclusionary criteria. Again, I excluded any studies that didn't use a cut point to determine tau positivity. So for example, if they used a clustering method to derive multiple subtypes of tau, those were excluded. And then finally, excluding studies that use an existing cut point for a total of 23 studies that derived a unique cut point using unique tau PET thresholding methods to their study. So I'm not going to go into every individual study, as there were 23 of them, but I want to just highlight that there was a lot of heterogeneity in terms of the methods used for these tau PET thresholding methods. So one difference was whether studies used partial volume correction to correct for those partial voluming effects from the choroid plexus or the CSF that can contaminate tau PET signal. So some studies did use it, some studies did not use it. And it seems that based on the literature, there's still debate in the field as to whether or not and when one should use partial volume correction. So that was one difference across studies. The reference region used for intensity normalization of the SUV, which is our main tau PET value that we get to measure signal intensity. So some studies using the cerebellar gray, some studies using cerebral white matter, and many other potential regions to use as that reference for intensity normalization. The region of interest was one thing that varied a lot across studies. So for example, some studies used a meta region of interest in the temporal lobe, some studies used approximation of Braak staging, and some studies used individual ROIs, such as the entorhinal cortex or the inferior temporal gyrus, all pretty much approximating that stereotypical Braak staging scheme, but a little bit different in terms of how early versus late it was within that staging scheme. And then the analytic approach widely varied across studies. So some analytic methods include receiver operating characteristic curves, some involved thresholding above a comparison group, some involved cluster analysis. And then even within those analytic types, there is variability. So for example, using an ROC method, you can vary the method you use to actually determine the cut point, whether you're maximizing sensitivity, whether you're maximizing what's called the Uden index. So really just a lot of variability here, as well as with the comparison group used as part of these analytic techniques. So for example, the comparison group could be amyloid negative, cognitively unimpaired individuals. It could be younger adults. It could be just cognitively unimpaired older adults or amyloid negative older adults. So when you put all these different things together across the 23 studies, all of these various decision points, you can see that there's a lot of room for variability in terms of how one determines tau PET positivity. I'm just going to go into a couple examples here from the studies I reviewed. So this is from a paper by Jack et al. In Lancet Neurology in 2017. Their sample consisted of 435 older adults from the Mayo Clinic study of aging. Their reference region was a cerebellar region, specifically the crust gray median. They did not use partial volume correction. The region of interest was a temporal meta region of interest composed of the amygdala, entorhinal, fusiform, parahippocampal, inferior temporal, and middle temporal regions. So kind of a composite of temporal regions. The analytic approach they used was ROC curves, maximizing accuracy with the comparison groups of younger adults and amyloid positive cognitively impaired older adults, resulting in a cut point, an SUVR of greater than 1.23. And here's an example of another study and how they differed on these various criteria or various methods that could be used. So this study was from Matz and Karlgren in Science Advances in 2020. Their sample consisted of 131 older adults from the BioFinder study, so a different sample composition here, although still amongst older adults. The reference region here instead was the inferior cerebellar gray specifically, in order again to create that SUVR, that intensity normalized value. They did not use partial volume correction. They examined 3 separate regions of interest: the entorhinal cortex, the inferior temporal gyrus, and a composite of Braak stage 5-6, so pretty widespread cortically. Their analytic approach was to determine the cut point based on a value that was 2 standard deviations above the mean of amyloid negative cognitively unimpaired group, with a cut point of various values for these different regions: 1.39 for the entorhinal cortex, 1.31 for the inferior temporal cortex, and 1.28 for the Braak stage 5-6 region. So you can see that even in just these two studies, there was a lot of differences in these different decision points used, which resulted, unsurprisingly, in different cut point values. So what I wanted to do is do an empirical follow-up to this systematic review, where I actually systematically varied some of these different variables in that more systematic way to actually compare those different methodological decision points within the same sample that went through the same pre-processing steps. So this study used a sample from the Alzheimer's Disease Neuroimaging Initiative, or ADNI, 785 older adults. And notably, all of this data was partial volume corrected and all used the inferior cerebellar gray reference region so that we could just have that standardized across these comparisons. So in a 2x2x2 design, I varied the region of interest, the analytic method, and the comparison group that was used. So that would result in ultimately 8 different ways of deriving these cut points. So the 2 regions of interest I used, one was the entorhinal cortex for really early stage tau deposition, and then that metatemporal region of interest that I mentioned from the Jack paper that was composed of a variety of temporal regions. For analytic method, I either used ROC curves or 2 standard deviations above the mean of the comparison group. And then for the comparison group, I either used all cognitively unimpaired individuals or only those cognitively unimpaired individuals who were also amyloid negative. So you can see here that results in these 4 different cells done both for the entorhinal cortex and the metatemporal region, which results in 8 different unique ways of deriving these cut points. And just of note here, I did, since I was interested in looking at comparing these different cut points on how they performed using various outcomes, I did split my sample into a training data set to create the cut points and then a test data set to actually test the cut points. So that was 510 individuals in the training data set and 275 individuals in the test data set in order to have those samples be independent and avoid any circularity. So I wanted to throw just a little bit of my code up here to show you what it looked like. So to create the cut points using those ROC curves, this is just an example of using the amyloid negative cognitively unimpaired comparison group and the metatemporal ROI. I use the packages optimal cut points and rocker. And you can see here that in the optimal cut points function, you insert your variable that you want to create the cut points for, your status or grouping variable that you want to use to identify the correct cut point, and then the specific method you wanted to use. Here I used Uden's index, which is sensitivity plus specificity -1. And here's just a depiction of the ROC curve, which you can get using this pred and prediction and performance functions from these packages. You can see that the area under the curve was 0.743, so pretty good classification accuracy. And then specifically it used maximization of Uden's index to determine the cut point that we would want to use to maximally differentiate individuals who are tau positive versus tau negative in terms of the sensitivity and specificity of those classifications. So this is a pretty busy table, and I'm going to break it down for you because this looks at those 8 different methods that I mentioned. So those methods are over here on the left. You can see that half the methods use the entorhinal cortex and half use the metatemporal region. Half used receiver operating characteristics, both within the meta ROI and the entorhinal region, and the other half using 2 standard deviations above the mean of the comparison group. And then half used a amyloid negative cognitively unimpaired comparison group, and the other half using just an overall cognitively unimpaired comparison group, resulting in these 8 methods here, each of which derived a unique cut point and a resultant unique tau positivity rate based on that cut point. So you can see that the cut points ranged pretty widely, ranging from a low of 1.64 to a high of 2.45. Unsurprisingly, you'll see that there was systematically a higher cut point within the entorhinal cortex, and that's because this is an earlier region of tau deposition, and there's some tau deposition even within individuals who undergo normal aging rather than a pathologic change. And so we have to have a higher cut point here to really differentiate those who are going to go on to progress, or rather those who have cognitive impairment versus those who do not. And you can see that, again, because we had different cut points here, we had pretty wide-ranging corresponding positivity rates as well, with a low of 13.9% using the meta-ROI 2 standard deviations above a cognitively unimpaired group, and a high of 38.7%, again, using the meta-ROI, the temporal ROI, but here using RSC analysis above an amyloid-negative cognitively unimpaired group. What I wanted to do next, which I'll get into in the following slides, was then compare these tau negative and tau positive groups for each of these different cut point methods in terms of how much those groups differed on these various outcomes, one being CSF p-tau, one being the mini mental state examination score or global cognition score, and one being a delayed memory recall score. So seeing which groups produce the largest difference in terms of these outcome variables as measured by Cohen's d. So here again, it's just a little bit of my code, very straightforward. I literally just was interested in looking at how the groups differed on this outcome, in this case, phosphorylated tau in the cerebrospinal fluid, grab the estimated marginal means and the pairwise comparisons for those two groups, and derived a Cohen's d based on that t-test. And then plotted these using a geom box plot function and a geom b-swarm function so that we can identify measures of central tendency and spread, as well as the individual data points themselves using that geom b-swarm function. So this is an example of using the method of 2 standard deviations above the amyloid negative, cognitively unimpaired group within the metatemporal region of interest. Unsurprisingly, the tau positive group, or tau PET positive group, had higher levels of CSF p-tau. That's what we expected, so that's good, that's in the right direction. And what I wanted to see is which cut point that derive different tau positive and tau negative groups produce the greatest discrepancy between these groups. So which cut point method was really maximally differentiating these two groups in terms of this outcome. Other outcomes I was interested in looking at were MMSE score and logical memory score. Again, unsurprisingly, the tau positive group was lower in terms of their overall cognition and their memory. And again, that Cohen's d was looking at which groups were, or which cut point method really maximally differentiated these groups in terms of these variables. So going back to that big chart, I want to draw your attention to some of the highest Cohen's d values here. So in terms of differentiating tau PET positive and negative groups on CSF p-tau, we can see that the best performance in terms of the Cohen's d that was the greatest absolute value was that meta-ROI region looking 2 standard deviations above the amyloid negative cognitively unimpaired group. For mini mental state exam, or MMSE, we can see that a few of the different cut point methods perform pretty similarly. And again, that meta-ROI 2 standard deviations above the amyloid negative cognitively unimpaired group was performing pretty well. And here for logical memory score, with the highest Cohen's d was looking at now the entorhinal cortex. But again, that same analytic method of looking 2 standard deviations above the amyloid negative cognitively unimpaired group. Now, I want to point out a few considerations, since I'm not necessarily providing recommendations to use any one of these methods, and I think it's really dependent on the specific research question asked. So one thing I want to bring up is whether we're interested in really identifying the sensitivity of tau positivity versus the specificity of these tau positivity designations. So are we interested in really identifying those people early on who are truly tau positive, and we want to try to capture as many of those tau positive individuals as possible without as much regard to false positives? versus if we're really interested in only identifying those who are tau positive and making sure we don't have any of those false positives in there. So those different decision points could result in different methods used in terms of whether we use different analytic approaches, whether we use different regions. So if we want a really sensitive early entorhinal cortex region versus better specificity, we might use a composite later stage region. I also want to bring up the point that there's a lot of benefit from using non-binary classification systems, as well as classification systems that identify non-traditional patterns of tau deposition. So I'm going to bring our attention to a study by Vogel et al. That was published recently in Nature Medicine that used the sustain model, a cluster analytic technique, to identify different subtypes of tau positivity. So they had this overall tau positive group split into these different classifications or these different subtypes. And you can see that a large portion of their sample fell into this pretty standard group, what we would expect from the stereotypical Braak staging, with medial temporal and lateral temporal and some inferior parietal tau deposition. But there was another large portion of their sample that was split into these other non-traditional tau PET patterns. So a group sparing the medial temporal lobe, a group with more of a posterior distribution, and a group with a more specific left temporal distribution. So just using those binary cut points misses a lot of this heterogeneity that we could have if we use different methods. Similarly, there's a lot of statistical downsides to changing a continuous variable into a categorical variable. So do we lose a lot of the richness of information we have from a continuous variable? That said, I believe there are situations where it's beneficial to have a cut point. For example, for entry into clinical trials, if we want to determine if people are positive or negative, we need that specific binary cut point in order to determine who is eligible versus who is ineligible. And one thing I want to consider, and I'd love to have a discussion at the end, is whether we should be careful with our use of amyloid status in the tau PET cut point derivation if we're going to go on to subsequently assess amyloid and tau positive and negative groups. So using that amyloid status, for example, as one of the comparison groups in the ROC or two standard deviation analyses, does that then go on and bias who's going to be put into the different amyloid and tau groupings? So now I'm going to shift gears a little bit and jump back into that ATN classification scheme to really bring your attention to these bottom boxes that I didn't mention earlier down here. So we can see that if individuals are tau positive but are amyloid negative, they're not characterized on the Alzheimer's continuum, but rather are characterized to have a non-Alzheimer's pathologic change. And again, you can see that over in the right here, that this red circle that's not overlapping with the yellow circle, which represents amyloid pathology, you can see that this red tau pathology circle, non-overlapping with the yellow circle, regardless of neurodegeneration status, is going to be labeled as non-Alzheimer's pathologic change. So my question is this A-T plus group truly a non-AD pathologic change, or could they reflect an early stage on the Alzheimer's continuum? This is from a study I was working on concurrently with the previous study I mentioned that's currently in press at Brain Communications. So in this study, I first categorized these amyloid and tau positive and negative groups, compared these groups on cognitive and biomarker outcomes, and compared these groups on associations between biomarkers and cognition. So this is just a depiction of how to categorize those two groups. So we can have individuals who are amyloid negative or positive and individuals who are tau negative or positive, resulting in these four possible groupings. Again, I didn't use neurodegeneration here. I was really focused on amyloid and tau positivity. And you can see that we have a A-T- group, or a no pathology group, two discordant groups, as I call them, where amyloid is positive and tau is negative, or conversely, amyloid is negative and tau is positive, or a group with both pathologies, A plus and T plus. So for this study, I again used data from the Alzheimer's Disease Neuroimaging Initiative, or ADNI, specifically 703 older adults without dementia. The predictor variable of interest was this AT positivity status group, so which of these 4 groups they fell into. You can see here the specific processing that was used for the amyloid PET using florbetapir, or I should have put in here, it was actually using florbetapir or florbetaben, and these 2 tracers were combined to maximize the sample size, and tau PET using flortaucipir. So importantly, I selected some cut points from the literature for this study in order to determine amyloid and tau positivity. As I just talked about, clearly selecting what cut point to use can really have a huge impact in the rest of your group categorizations and resultant group comparisons. So for amyloid, since florbetapir and florbetaben were combined, we used a conversion into a centiloid unit to standardize across those 2 tracers. And the cut point was determined to be 28.8, which was from the literature, a cut point that maximized Udin's index based on CSF amyloid / p-tau positivity. For tau PET, I selected a cut point of 1.23 from that JACC Lancet Neurology paper I mentioned earlier that maximizes accuracy based on younger controls versus amyloid positive cognitively impaired older adults. And you'll see that this cut point used here is lower than all the ones that I derived within the empirical comparison that I just went over. And here I was really interested in identifying people who were potentially early on in terms of their tau deposition to show people who, a grouping who had this early tau deposition that may go on to progress into Alzheimer's. So really maximizing that sensitivity of determining who's tau positive, resulting in a more liberal cut point of 1.23 in terms of the selection here. There was a number of outcome variables I looked at, including demographic variables, vascular risk variables, neuropsychological performance across 6 tests of verbal memory, language, and attention/executive function, subjective cognition using the Everyday Cognition Questionnaire, again in the domains of memory, language, and executive function, and cortical thickness across a number of temporal, parietal, and frontal regions. Statistics were pretty straightforward for this paper. So any amyloid tau group comparisons on a binary variable were looked at using chi-square tests. ANOVAs or ANCOVAs were used to compare groups on continuous variables of interest, adjusting for age, sex, education, for cognitive outcomes, and ApoE4 status. And then multiple linear regression models to assess for the association between memory scores and entorhinal and inferior temporal cortical thickness within these amyloid and tau groups. So here's just a breakdown of those groupings. First and foremost, you can see that the majority of the sample fell into the amyloid negative, tau negative, or no pathology group. About half the sample fell into that group. Another 27% fell conversely into the both pathology group, or the A+T+ group. But we had a sizable portion of the sample that fell into these 2 discordant groups, amyloid plus and T minus, or amyloid negative and tau positive. And I'm really going to focus, for the purpose of group comparisons, on this group that's purported to be a non-AD pathologic change to see which groups they look most similar to. If this group looks most similar to the no pathology group, that would indicate that perhaps they are truly more of a non-Alzheimer's pathologic change or a primary aging pathologic process, such as primary aging related tauopathy or PART. Versus if the A-T+ group looks more like these amyloid positive groups, which are proposed to be on the Alzheimer's continuum, then perhaps that's indicative that this group should be more strongly considered and perhaps be considered to be on the Alzheimer's continuum as well. So here's just some basic group comparisons on amyloid PET and tau PET values. I used rain cloud plots here, and I have the code over on the left for anyone who's interested. But essentially what I want to draw your attention to is on the left here are those amyloid tau groupings. On the x-axis are either their amyloid PET values or their tau PET values. You can see there's sharp distinctions here between the groups because of the cut points used. That necessitated that these groups did not overlap in terms of their tau or their amyloid levels. And what I want to draw your attention to in particular is that this A-T plus group had a pretty broad range of amyloid PET values, at least as broad as the A-T minus group. So it wasn't necessarily that this group was all sub-threshold amyloid accumulation, but rather they had a pretty broad range. Just looking at some of the more basic demographic variables, we found that the amyloid negative, tau negative, or no pathology group was younger than other groups. The both pathology group had lower educational attainment than other groups, as well as higher depressive levels than 2 of the other groups, but not the amyloid negative, tau positive group. Unsurprisingly, the highest rate of mild cognitive impairment was amongst the both pathology group, with similar rates amongst the 3 other groups. The highest rate of ApoE4 positivity was in the both pathology group, followed by the A plus T minus group, with similar rates in both of the amyloid negative groups. And there were no group differences in terms of sex/gender distribution, race in terms of categorized as white versus non-white, although as I'll note shortly, the sample was very predominantly white. No group differences in terms of any of the vascular risk variables assessed. So Hodgkinski risk level, pulse pressure, or white matter hyperintensity volumes, suggesting that any group differences we see subsequently likely aren't attributable to differences in vascular risk. Here's just another example of some of the code used. Again, a pretty straightforward linear regression model here, looking at a cognitive variable here as the outcome, with age, education, gender, and ApoE positivity as the covariates, and that amyloid tau status variable as the predictor of interest. And then again, I used those B-swarm plots and overlaid on box plots to depict the group differences. So in terms of our neuropsychological variables, we have the memory variables here up top, the language variables here in the middle, and the attention/executive function variables here at the bottom. And what I first want to draw your attention to is the fact that the A plus T plus, or both pathology group, unsurprisingly had lower scores across the board, across all domains assessed. But interestingly, the A minus T plus group, or amyloid negative tau positive group, had lower scores than the no pathology group in terms of their memory recall and their naming, a language measure sensitive to early changes in Alzheimer's disease. So they're already showing some potentially subtle cognitive compromises relative to the no pathology group, which the A plus T minus group was not showing. The A plus T minus group was lower, however, on a measure of executive function. When we look at self-reported cognition, we again see that the A plus T group is reporting the highest degree of impairment across memory, language, and executive function in terms of self-report. And the A plus T minus group is also showing high report of language dysfunction. The A minus T plus group here did not report any differences in self-reported cognition, despite those observed differences from the no pathology group in terms of memory and language. In terms of cortical thickness, we can see that the A plus T plus group was systematically lower than the A minus T minus group, or no pathology group, across the entorhinal cortex, the inferior temporal gyrus, and the precuneus, but not the frontal, superior frontal gyrus. And the A minus T plus group was also lower than the no pathology group in terms of their entorhinal cortex thickness, but not these other regions assessed. Now, finally, I looked at within group associations between either the entorhinal cortex or the inferior temporal gyrus, and memory recall and memory recognition. And what we can see here is pretty systematically that we're seeing this greenish bluish A minus T plus group and the yellow A plus T plus group, so both of the tau positive groups, regardless of amyloid status, are showing the expected positive associations between temporal thickness and memory performance. Whereas the other groups, both of the amyloid positive groups, regardless of tau status, aren't showing any consistent associations with these variables. So some implications and conclusions. A sizable portion of the sample were classified as A minus T plus, or 13.5% of the sample. So this is not really a negligible group that falls into this classification. This A minus T plus group demonstrated poor verbal memory, poor naming, and lower entorhinal cortical thickness relative to the no pathology group. Associations between memory and temporal regions were only observed in the A minus T plus group and the A plus T plus groups. And as I mentioned earlier, that A minus T plus group did not have higher vascular risk than other groups, suggesting that that's not driving the differences in these cognitive and neurodegeneration or cortical thickness variables. One thing I want to be sure to mention here is that this study and both of these studies were conducted in the Alzheimer's Disease Neuroimaging Initiative, which is a largely healthy, highly educated, predominantly white sample. So I want to be really careful in making sure that these conclusions aren't generalized to samples with more diversity in terms of race, ethnicity, educational attainment, SES, disability, etc. And this work definitely needs to be replicated in more diverse samples. So now some questions I want to leave us with. Does this A minus T plus classification reflect an early stage on the Alzheimer's continuum, or are they better characterized as per the ATN scheme as a non-AD pathologic change? And given minimal differences between the A minus T plus and A plus T minus groups, should there really be a distinction in the nomenclature used for these two groups? Should we consider cognitive and clinical features in addition to biomarker status, as I showed with these neuropsychological scores and these self-reported memory scores, to be pretty important in distinguishing these groups? And is the exclusion of amyloid negative and tau positive individuals from research and clinical trials harmful to the advancement of our understanding of Alzheimer's disease, since these individuals, not being amyloid positive, are often excluded from these research studies? And with that, I want to thank you all for listening and open it up for discussion.
All right, Alex, thank you so much. That was really excellent work. For anybody who has questions, you can type them into the chat or just go ahead and unmute yourself and you can ask the questions live to Alex. So go ahead and do so if you are so inclined. So Alex, we have one question coming in now. What software did you use to process your imaging data and why? And did you do your coding in Python or was it in a different language?
This is a very good question that I unfortunately don't have the answer to, and I should have put that disclaimer on, that I did not do any of the processing of these data. This data was all processed in ADNI, and so it was all processed specifically by the UCSF group. So all of that documentation is available on the ADNI website online, but I unfortunately don't know the details of it. I was more on the back end of the data analysis after it had been pre-processed. And I did my coding in R, sorry.
Sorry. And we'll take our next question from Lars, who I think wants to ask live. So Lars, go ahead.
Thank you for an excellent presentation. So I have a number of questions so I'm very interested in hearing your thoughts on. So I think the first one is a bit provocative, but it's really a question to say, why dichotomize? Why define something called T plus at all? It's according to the understanding of disease, and you can say the Cliff Jack NIA classification and so forth. It's not, you know, it's the amyloid that puts you on the Alzheimer's continuum. So what is the purpose of the T plus? Could we do without it?
It's a really good question. And the whole dichotomization of both these variables haunted me a little bit throughout both of these studies, just because we do lose so much rich information by creating these dichotomous groups. And it is somewhat arbitrary, our selection of these groups and who's positive and who's negative. I do think there's value moving forward in looking at these AT groups specifically, so groups who have this combination of amyloid and or tau positivity, specifically the discordant groups, in terms of selection into clinical trials. So I think that we can see that just dichotomizing based on amyloid positivity, those two amyloid positive groups weren't really showing, or I should say the amyloid positive tau negative group wasn't really showing changes in terms of neuropsychological performance, cortical thickness, associations between these two. Whereas dichotomizing based on tau positivity, those groups were showing these changes. So I do think there's value in looking at dichotomization of the tau group for certain select situations that require that dichotomous value for something like eligibility for a clinical trial. And I do think that doing that for tau adds information above and beyond what you would find for amyloid, given that that amyloid positive group, if you don't look at their tau status, they're pretty heterogeneous in terms of their presentation. So adding in that T value in there, I think really adds some important information.
Yeah, so following up on that actually leads up to another question. So I'm not sure I caught it exactly, but your cutoff for tau PET positivity, was that based on entorhinal cortex SUVR?
For this study looking at the amyloid negative and tau positive groups, or amyloid tau groups, that was based on a metatemporal region of interest. Okay. That's a good question. Yes. So it was a lower cut point, but it was based on a more reliable, somewhat later stage composite, as opposed to looking at the entorhinal cortex.
Yeah. Okay. So thanks. But I was just thinking that because it's a lower cut point, mm-hmm. you will of course also probably get more false positives. So the group may seem bigger right. than it actually is. So I think that there are work, especially with other tau tracers, that point to the fact that there more or less exist no people that are A minus T plus when you use conventional cutoffs.
I agree that there are likely some false positives in there. And that was some of the danger of using that lower cut point in this study. I really was focused on identifying as many people as I could who were tau positive, especially to get that discordant group, rather than being more conservative with the cut point. But I imagine that A minus T plus group is pretty heterogeneous in terms of whether some of them may be considered to be on the Alzheimer's trajectory versus others may be a non-AD pathologic change versus others may be normal aging. And I think that's why we're not seeing sharp distinctions in the cognitive scores, but rather some subtle distinctions, because I think it's in reality probably only a portion of that group who are likely on an Alzheimer's trajectory, given that potential for false positives.
Thank you.
Thank you. Excellent questions.
Alex, we had one question come in through the chat. How do you distinguish the amyloid negative tau positive individuals from general tauopathies such as FTD and things of that sort? And do you think this is an important consideration when we're trying to clarify the Alzheimer's continuum?
I do think that's a really excellent point. The potential for non-Alzheimer's or non-traditional Alzheimer's pathologies to be considered within that A minus T plus group. I think one way we can potentially distinguish that is based on our region of interest that we used. So I do think that metatemporal region is a little bit more specific to Alzheimer's disease, although there certainly can be tau deposition there, and frontotemporal dementia, especially some of the more language-based variants that are more temporally based. But I think that's an excellent question, and I don't think we can fully distinguish, as I just mentioned with Lars, that I think there's a lot of heterogeneity in that A minus T plus group, such that some may have these non-AD pathologies. And if we're trying to better understand those who are on the Alzheimer's continuum, it's true that amyloid does certainly give us some important information. And we could see that those who were amyloid positive and tau positive both really were showing consistently the lowest neuropsychological scores, the most concern in terms of their self-reported memory, and the most cortical thinning across all other groups. So I do think that A+ group, or I do think that A+ designation is still important to consider. My main takeaway is just for us to not ignore this A-T+ group in research. And I think we can do other things to potentially determine which of these are more likely on an Alzheimer's trajectory. Those who are E4 positive, those who are having specific memory complaints, as well as and or memory concerns and on objective testing as opposed to language or executive function concerns. So that's where we can implement these clinical and cognitive features into this A-T+ or AT designations, having like an ATC, so to speak, where we incorporate cognition to try to better characterize those who are likely on an Alzheimer's trajectory versus a separate pathologic process.
Thank you, Alex. And one of our attendees, Mohammed, I would like to ask some questions live. So Mohammed, go ahead.
Hi, Alex. How are you doing? It was a great presentation, by the way.
Thank you.
Couple of questions is, when you separated your groups into training and testing, was randomization done? How many times did you randomize the groups into testing and training?
Yes, good question. It was randomly done. I don't remember the exact details, but they were randomly selected into testing and training data sets.
But how many times was that process repeated?
I do not remember off the top of my head, I will admit.
Okay, because I wanted to ask if the randomization had an effect on your cutoffs.
Oh, that's a good question. Yes. Do you want to explain more about that?
Yeah, so if you randomize your groups differently, would your cutoffs be different if you use a different random, and what is the spread in the cutoff that you would see if you randomized it maybe 1,000 times?
Yeah, so that's something that I didn't do, is randomizing that many times in terms of for the purpose of comparing different cut point values and the range of cut point values that would come out. But that's something that could be a really good follow-up to do. I appreciate that suggestion, because you're right that the randomization could have resulted in slightly different cut points just based on the selection of which of those 510 participants were used in the training data set.
Another question is, do you know if how the internal cortex was segmented?
It was segmented using free surfer segmentation, I believe.
And then how was the registration to the PET done?
I do not remember the details of that, unfortunately.
Because we have seen that even free surfer has a hard job in segmenting the internal cortex, and using that can have effects on your values, SUV as determined in that region. And if the segmentation or registration has issues, then those get reflected in the mean tau values from those regions. And that's where partial volume effects come very handy to do.
Absolutely. I do think the entorhinal cortex is a little bit of a dangerous region to use for those partial volume regions, as well as it's just such a small region susceptible to a lot of noise essentially in the pre-processing that can be done, which of course is going to vary or result in varied tau signal and tau positivity rates. So that's why I elected for this follow-up study, this A+T- or A-T+ study, to look at that metatemporal composite for just a little more reliability in terms of looking across multiple regions and not just that entorhinal cortex region, because you bring up a great point that there's a lot of methodological concerns with that region in terms of the pre-processing.
Something else is, when you did your cutoffs, was age taken as a covariate?
Age was not taken as a covariate in the cutoffs, no. So it was just based on discriminating those A- cognitively unimpaired or all cognitively unimpaired groups, but age wasn't taken into account, just their cognitive status and or their amyloid status.
Okay.
Thank you for the question.
Those are the questions I had, basically. Thank you for answering.
Thank you so much.
All right, well, Alex, there are no more questions coming through the chat. And if there are no more questions that anybody has live, we'll go ahead and end for today. I do appreciate Alex, once again, you taking the time to present your work to us. And, I really enjoyed the conversations and the questions that we had from it. For everybody, the recording for this webinar will be available later today, and I will send out the link to it for all those who registered for this webinar. So thank you all again very much, and hopefully soon we'll be able to send an email letting you know who our speaker will be for January. Thank you very much, and enjoy your weekends.
Thank you, everyone.
Thanks, Alex.